A nuclear power plant is a thermal power station in which the heat source is a nuclear reactor. As is typical in all conventional thermal power stations, the heat is used to generate steam, which drives a steam turbine connected to a generator which produces electricity. As of April 23, 2014, the IAEA report there are 435 nuclear power reactors in operation operating in 31 countries. Nuclear power plants are usually considered to be base load stations, since fuel is a small part of the cost of production. History. For more history, see nuclear reactor, nuclear power and nuclear fission. Electricity was generated by a nuclear reactor for the first time ever on September 3, 1948 at the X-10 graphite reactor in Oak Ridge, Tennessee in the United States, and was the first nuclear power plant to power a light bulb. The second, larger experiment occurred on December 20, 1951 at the EBRI experimental station near Arco, Idaho in the United States. On June 27, 1954, the world's first nuclear power plant to generate electricity for a power grid started operations at the Soviet city of Obninsk. The world's first full-scale power station, Calder Hall in England, opened on October 17, 1956. Systems. This section has recently been translated from the German Wikipedia. The conversion to electrical energy takes place indirectly, as in conventional thermal power plants. The heat is produced by fission in a nuclear reactor. Directly or indirectly, water vapor is produced. The pressurized steam is then usually fed to a multi-stage steam turbine. Steam turbines in Western nuclear power plants are among the largest steam turbines ever. After the steam turbine has expanded and partially condensed the steam, the remaining vapor is condensed in a condenser. The condenser is a heat exchanger which is connected to a secondary side such as a river or a cooling tower. The water is then pumped back into the nuclear reactor and the cycle begins again. The water-steam cycle corresponds to the Rankine cycle. Nuclear reactors. A nuclear reactor is a device to initiate and control a sustained nuclear chain reaction. The most common use of nuclear reactors is for the generation of electric energy and for the propulsion of ships. The nuclear reactor is the heart of the plant. In its central part, the reactor core's heat is generated by controlled nuclear fission. With this heat, a coolant is heated as it is pumped through the reactor and thereby removes the energy from the reactor. Heat from nuclear fission is used to raise steam, which runs through turbines, which in turn powers either ships' propellers or electrical generators. Since nuclear fission creates radioactivity, the reactor core is surrounded by a protective shield. This containment absorbs radiation and prevents radioactive material from being released into the environment. In addition, many reactors are equipped with a dome of concrete to protect the reactor against both internal casualties and external impacts. In nuclear power plants, different types of reactors, nuclear fuels, and cooling circuits and moderators are used. Steam turbine. The purpose of the steam turbine is to convert the heat contained in steam into mechanical energy. The engine house with the steam turbine is usually structurally separated from the main reactor building. It is so aligned to prevent debris from the destruction of a turbine in operation from flying towards the reactor. In the case of a pressurized water reactor, the steam turbine is separated from the nuclear system. To detect a leak in the steam generator and thus the passage of radioactive water at an early stage, an activity meter is mounted to track the outlet steam of the steam generator. In contrast, boiling water reactors pass radioactive water through the steam turbine, so the turbine is kept as part of the control area of the nuclear power plant. Generator. The generator converts kinetic energy supplied by the turbine into electrical energy. Low-pole AC synchronous generators of high-rated power are used. Cooling system. A cooling system removes heat from the reactor core and transports it to another area of the plant, where the thermal energy can be harnessed to produce electricity or to do other useful work. Typically the hot coolant is used as a heat source for a boiler, and the pressurized steam from that boiler powers one or more steam turbine-driven electrical generators. Safety valves. In the event of an emergency, Safety valves can be used to prevent pipes from bursting or the reactor from exploding. The valves are designed so that they can derive all of the supplied flow rates with little increase in pressure. In the case of the BWR, the steam is directed into the suppression chamber and condenses there. The chambers on a heat exchanger are connected to the intermediate cooling circuit. Feedwater pump. The water level in the steam generator and nuclear reactor is controlled using the feedwater system. The feedwater pump has the task of taking the water from the condensate system, increasing the pressure and forcing it into either the steam generators or directly into the reactor. Emergency power supply. Most nuclear plants require two distinct sources of off-site power feeding station service transformers that are sufficiently separated in the plant switchyard and can receive power from multiple transmission lines. In addition, in some nuclear plants the turbine generator can power the plant's house loads while the plant is online via station service transformers which tap power from the generator output busbars before they reach the step-up transformer. Even with a redundancy of two power sources, total loss of off-site power is still possible. Nuclear power plants are equipped with emergency power systems to maintain safety in the event of unit shutdown and loss of off-site power. Batteries provide uninterruptible power to instrumentation, control systems, and valves. Emergency diesel generators provide direct AC power to charge the batteries and to provide power to systems requiring AC power such as motor-driven pumps. The emergency diesel generators do not power all plant systems, only those required to shut the reactor down safely, remove decay heat from the reactor, provide emergency core cooling, and, in some plants, spent fuel pool cooling. The large power generation pumps such as the main feedwater, condensate, circulating water, and reactor coolant pumps are not backed up by the diesels. People in a nuclear power plant, nuclear engineers, reactor operators, health physicists, emergency response team personnel, Nuclear Regulatory Commission resident inspectors. In the United States and Canada, workers except for management, professional and security personnel are likely to be members of either the International Brotherhood of Electrical Workers or the Utility Workers Union of America, or one of the various trades and labor unions representing machinist, laborers, boilermakers, millwrights, iron workers etc. Economics. The economics of new nuclear power plants is a controversial subject, and multi-billion-dollar investments ride on the choice of an energy source. Nuclear power plants typically have high capital costs, but low direct fuel costs, with the costs of fuel extraction, processing, use and spent fuel storage internalized costs. Therefore, comparison with other power generation methods is strongly dependent on assumptions about construction timescales and capital financing for nuclear plants. Cost estimates take into account plant decommissioning and nuclear waste storage or recycling costs in the United States due to the Price-Anderson Act. With the prospect that all spent nuclear fuel/nuclear waste could potentially be recycled by using future reactors, Generation 4 reactors, that are being designed to completely close the nuclear fuel cycle. On the other hand, construction, or capital cost aside, measures to mitigate global warming such as a carbon tax or carbon emissions trading, increasingly favor the economics of nuclear power. Further efficiencies are hoped to be achieved through more advanced reactor designs. Generation 3 reactors promise to be at least 17% more fuel efficient, and have lower capital costs, while futuristic Generation 4 reactors promise 10,000 to 30,000% greater fuel efficiency and the elimination of nuclear waste. In Eastern Europe, a number of long-established projects are struggling to find finance, notably Belin in Bulgaria and the additional reactors at Cernavoda in Romania, and some potential backers have pulled out. Where cheap gas is available and its future supply relatively secure, this also poses a major problem for nuclear projects. Analysis of the economics of nuclear power must take into account who bears the risks of future uncertainties. To date, all operating nuclear power plants were developed by state-owned or regulated utility monopolies where many of the risks associated with construction costs, operating performance, fuel price, and other factors were borne by consumers rather than suppliers. Many countries have now liberalized the electricity market where these risks, and the risk of cheaper competitors emerging before capital costs are recovered, are borne by plant suppliers and operators rather than consumers, which leads to a significantly different evaluation of the economics of new nuclear power plants. Following the 2011 Fukushima I nuclear accidents, costs are likely to go up for currently operating and new nuclear power plants, due to increased requirements for on-site spent fuel management and elevated design basis threats. However, many designs, such as the currently under construction April 1000, use passive nuclear safety cooling systems, unlike those of Fukushima I which required active cooling systems. This largely eliminates the necessity to spend more on redundant backup safety equipment. Safety and accidents. There are trades to be made among safety, economic and technical properties of different reactor designs for particular applications. Historically, these decisions were often made in private by scientists, regulators and engineers, but this may be considered problematic, and since Chernobyl and 3 Mile Island, many involved now consider free prior informed consent and morality to be primary considerations. In his book, Normal Accidents, Charles Perrow says that multiple and unexpected failures are built into society's complex and tightly coupled nuclear reactor systems. Such accidents are unavoidable and cannot be designed around. An interdisciplinary team from MIT has estimated that given the expected growth of nuclear power from 2005 to 2055, at least 4 serious nuclear accidents would be expected in that period. However, the MIT study does not take into account improvements in safety since 1970. To date, there have been 5 serious accidents in the world since 1970, corresponding to the beginning of the operation of Generation II reactors. This leads to on average 1 serious accident happening every 8 years worldwide. Complexity. Nuclear power plants are some of the most sophisticated and complex energy systems ever designed. Any complex system, no matter how well it is designed and engineered, cannot be deemed failure-proof. Veteran journalist and author Stephanie Cook has argued. The reactors themselves were enormously complex machines with an incalculable number of things that could go wrong. When that happened at 3 Mile Island in 1979, another fault line in the nuclear world was exposed. One malfunction led to another, and then to a series of others, until the core of the reactor itself began to melt, and even the world's most highly trained nuclear engineers did not know how to respond. The accident revealed serious deficiencies in a system that was meant to protect public health and safety. The 1979 3 Mile Island accident inspired Perrow's book Normal Accidents, where a nuclear accident occurs, resulting from an unanticipated interaction of multiple failures in a complex system. TMI was an example of a normal accident because it was unexpected, incomprehensible, uncontrollable and unavoidable. Perrow concluded that the failure at 3 Mile Island was a consequence of the system's immense complexity. Such modern high-risk systems, he realized, were prone to failures however well they were managed. It was inevitable that they would eventually suffer what he termed a normal accident. Therefore, he suggested, we might do better to contemplate a radical redesign, or if that was not possible, to abandon such technology entirely. A fundamental issue contributing to a nuclear power system's complexity is its extremely long lifetime. The time frame from the start of construction of a commercial nuclear power station through the safe disposal of its last radioactive waste, may be 100 to 150 years. Failure modes of nuclear power plants. There are concerns that a combination of human and mechanical error at a nuclear facility could result in significant harm to people and the environment. Operating nuclear reactors contain large amounts of radioactive fission products which, if dispersed, can pose a direct radiation hazard, contaminate soil and vegetation, and be ingested by humans and animals. Human exposure at high enough levels can cause both short-term illness and death and longer-term death by cancer and other diseases. It is impossible for a commercial nuclear reactor to explode like a nuclear bomb since the fuel is never sufficiently enriched for this to occur. Nuclear reactors can fail in a variety of ways. Should the instability of the nuclear material generate unexpected behavior, it may result in an uncontrolled power excursion. Normally, the cooling system in a reactor is designed to be able to handle the excess heat this causes. However, should the reactor also experience a loss of coolant accident, then the fuel may melt or cause the vessel in which it is contained to overheat and melt. This event is called a nuclear meltdown. After shutting down, for some time the reactor still needs external energy to power its cooling systems. Normally this energy is provided by the power grid to which that plant is connected, or by emergency diesel generators. Failure to provide power for the cooling systems, as happened in Fukushima I, can cause serious accidents. Nuclear safety rules in the United States do not adequately weigh the risk of a single event that would knock out electricity from the grid and from emergency generators, as a quake and tsunami recently did in Japan, Nuclear Regulatory Commission officials said in June 2011. Vulnerability of nuclear plants to attack. Nuclear reactors become preferred targets during military conflict and, over the past 3 decades, have been repeatedly attacked during military airstrikes, occupations, invasions and campaigns. In September 1980, Iran bombed the Al-Dawayh nuclear complex in Iraq, in Operation Scorched Sword. In June 1981, an Israeli airstrike completely destroyed Iraq's unregistered trademark Ozark nuclear research facility. Between 1984 and 1987, Iraq bombed Iran unregistered trademark Bushehr nuclear plant 6 times. On January 8, 1982, Controversies, the armed wing of the ANC, attacked South Africa's Koeberg nuclear power plant while it was still under construction. In 1991, the U.S. bombed 3 nuclear reactors and an enrichment pilot facility in Iraq. In 1991, Iraq launched Scud missiles at Israeli unregistered trademark Dimona nuclear power plant. In September 2007, Israel bombed a Syrian reactor under construction. In the U.S., plants are surrounded by a double row of tall fences which are electronically monitored. The plant grounds are patrolled by a sizable force of armed guards. The NRC's design basis threat criteria for plants is a secret, and so what size of attacking force the plants are able to protect against is unknown. However, to scram a plant takes fewer than 5 seconds while unimpeded restart takes hours, severely hampering a terrorist force in a goal to release radioactivity. Attack from the air is an issue that has been highlighted since the September 11 attacks in the U.S. However, it was in 1972 when 3 hijackers took control of a domestic passenger flight along the east coast of the U.S. and threatened to crash the plane into a U.S. nuclear weapons plant in Oak Ridge, Tennessee. The plane got as close as 8,000 feet above the site before the hijackers' unregistered trademark demands were met. The most important barrier against the release of radioactivity in the event of an aircraft strike on a nuclear power plant is the containment building and its missile shield. Current NRC Chairman Dale Klein has said nuclear power plants are inherently robust structures that our studies show provide adequate protection in a hypothetical attack by an airplane. The NRC has also taken actions that require nuclear power plant operators to be able to manage large fires or explosions no matter what has caused them. In addition, supporters point to large studies carried out by the U.S. Electric Power Research Institute that tested the robustness of both reactor and waste fuel storage and found that they should be able to sustain a terrorist attack comparable to the September 11 terrorist attacks in the U.S. Spent fuel is usually housed inside of the plant's protected zone, or a spent nuclear fuel shipping cask. Stealing it for use in a dirty bomb would be extremely difficult. Exposure to the intense radiation would almost certainly quickly incapacitate or kill anyone who attempts to do so. Plant location. In many countries, plants are often located on the coast, in order to provide a ready source of cooling water for the essential surface water system. As a consequence, the design needs to take the risk of flooding and tsunamis into account. The World Energy Council argues disaster risks are changing and increasing the likelihood of disasters such as earthquakes, cyclones, hurricanes, typhoons, flooding. High temperatures, low precipitation levels and severe droughts may lead to freshwater shortages. Seawater is corrosive and so nuclear energy supply is likely to be negatively affected by the freshwater shortage. This generic problem may become increasingly significant over time. Failure to calculate the risk of flooding correctly led to a Level 2 events on the International Nuclear Event Scale during the 1999 Blyea nuclear power plant flood, while flooding caused by the 2011 Tohoku earthquake and tsunami led to the Fukushima I nuclear accidents. The design of plants located in seismically active zones also requires the risk of earthquakes and tsunamis to be taken into account. Japan, India, China and the USA are among the countries to have plants in earthquake-prone regions. Damage caused to Japan's Kashiwazaki-Kariwa nuclear power plant during the 2007 Kaetsu offshore earthquake underline concerns expressed by experts in Japan prior to the Fukushima accidents, who have warned of a Genpatsu Shinsai. Multiple reactors. The Fukushima nuclear disaster illustrated the dangers of building multiple nuclear reactor units close to one another. This proximity triggered the parallel, chain reaction accidents that led to hydrogen explosions damaging reactor buildings and water draining from open-air spent fuel pools, a situation that was potentially more dangerous than the loss of reactor cooling itself. Because of the closeness of the reactors, Plant Director Masao Yoshida was put in the position of trying to cope simultaneously with core meltdowns at 3 reactors and exposed fuel pools at 3 units. Nuclear safety systems. The 3 primary objectives of nuclear safety systems as defined by the Nuclear Regulatory Commission are to shut down the reactor, maintain it in a shutdown condition, and prevent the release of radioactive material during events and accidents. These objectives are accomplished using a variety of equipment, which is part of different systems, of which each performs specific functions. Routine emissions of radioactive materials. During everyday routine operations, emissions of radioactive materials from nuclear plants are released to the outside of the plants, although they are quite slight amounts. The daily emissions go into the air, water and soil. NRC says, nuclear power plants sometimes release radioactive gases and liquids into the environment under controlled, monitored conditions to ensure that they pose no danger to the public or the environment, and routine emissions during normal operation of a nuclear power plant are never lethal. According to the United Nations, regular nuclear power plant operation including the nuclear fuel cycle amounts to 0.0002 MSV annually in average public radiation exposure. The legacy of the Chernobyl disaster is 0.002 MSV or as a global average as of a 2008 report. A natural radiation exposure averages 2.4 MSV annually, although frequently varying depending on an individual's location from 1 to 13 MSV. The Japanese myth of absolute safety. In Japan, many government agencies and nuclear companies have promoted a public myth of absolute safety that nuclear power proponents had nurtured over decades. The tsunami that began the Fukushima nuclear disaster could have been anticipated, and in March 2012, Prime Minister Yoshihiko Noda acknowledged that the Japanese government shared the blame for the Fukushima disaster, saying that officials had been blinded to the country's technological infallibility, and were all too steeped in a safety myth. In Japan, a national program to develop robots for use in nuclear emergencies was terminated in midstream because it smacked too much of underlying danger. Japan, supposedly a major power in robotics, had none to send into Fukushima during the disaster. Similarly, Japan unregistered trademark as Nuclear Safety Commission stipulated in its safety guidelines for light water nuclear facilities that a potential for extended loss of power need not be considered however, it was exactly such an extended loss of power to the cooling pumps that caused the meltdown at the Fukushima nuclear facilities. Controversy. The nuclear power debate is about the controversy which has surrounded the deployment and use of nuclear fission reactors to generate electricity from nuclear fuel for civilian purposes. The debate about nuclear power peaked during the 1970s and 1980s, when it reached an intensity unprecedented in the history of technology controversies, in some countries. Proponents argue that nuclear power is a sustainable energy source which reduces carbon emissions and can increase energy security if its use supplants a dependence on imported fuels. Proponents advance the notion that nuclear power produces virtually no air pollution, in contrast to the chief viable alternative of fossil fuel. Proponents also believe that nuclear power is the only viable course to achieve energy independence for most Western countries. They emphasize that the risks of storing waste are small and can be further reduced by using the latest technology in newer reactors, and the operational safety record in the Western world is excellent when compared to the other major kinds of power plants. Opponents say that nuclear power poses many threats to people and the environment. These threats include health risks and environmental damage from uranium mining, processing and transport, the risk of nuclear weapons proliferation or sabotage, and the unsolved problem of radioactive nuclear waste. They also contend that reactors themselves are enormously complex machines where many things can and do go wrong, and there have been many serious nuclear accidents. Critics do not believe that these risks can be reduced through new technology. They argue that when all the energy-intensive stages of the nuclear fuel chain are considered, from uranium mining to nuclear decommissioning, nuclear power is not a low-carbon electricity source. Reprocessing. Nuclear reprocessing technology was developed to chemically separate and recover fissionable plutonium from irradiated nuclear fuel. Reprocessing serves multiple purposes, whose relative importance has changed over time. Originally, reprocessing was used solely to extract plutonium for producing nuclear weapons. With the commercialization of nuclear power, the reprocessed plutonium was recycled back into MOX nuclear fuel for thermal reactors. The reprocessed uranium, which constitutes the bulk of the spent fuel material, can in principle also be reused as fuel, but that is only economic when uranium prices are high or disposal is expensive. Finally, the breeder reactor can employ not only the recycled plutonium and uranium in spent fuel, but all the actinides, closing the nuclear fuel cycle and potentially multiplying the energy extracted from natural uranium by more than 60 times. Nuclear reprocessing reduces the volume of high-level waste, but by itself does not reduce radioactivity or heat generation and therefore does not eliminate the need for a geological waste repository. Reprocessing has been politically controversial because of the potential to contribute to nuclear proliferation, the potential vulnerability to nuclear terrorism, the political challenges of repository siting, and because of its high cost compared to the once-through fuel cycle. In the United States, the Obama administration stepped back from President Bush's plans for commercial-scale reprocessing and reverted to a program focused on reprocessing-related scientific research. Accident indemnification. The Vienna Convention on Civil Liability for Nuclear Damage puts in place an international framework for nuclear liability. However, states with the majority of the world's nuclear power plants, including the US, Russia, China and Japan, are not party to international nuclear liability conventions. In the US, insurance for nuclear or radiological incidents is covered by the Price-Anderson Nuclear Industries Indemnity Act. Under the energy policy of the United Kingdom through its Nuclear Installations Act of 1965, liability is governed for nuclear damage for which a UK nuclear licensee is responsible. The Act requires compensation to be paid for damage up to a limit of £150 million by the liable operator for 10 years after the incident. Between 10 and 30 years afterwards, the government meets this obligation. The government is also liable for additional limited cross-border liability under international conventions. Decommissioning. Nuclear decommissioning is the dismantling of a nuclear power plant and decontamination of the site to a state no longer requiring protection from radiation for the general public. The main difference from the dismantling of other power plants is the presence of radioactive material that requires special precautions. Warranty period of operation of nuclear power plants is 30 years. One from factors whereas the destruction of the reactors shall under the action of ionizing radiation. Generally speaking, nuclear plants were designed for a life of about 30 years. Newer plants are designed for a 40 to 60-year operating life. Decommissioning involves many administrative and technical actions. It includes all cleanup of radioactivity and progressive demolition of the plant. Once a facility is decommissioned, there should no longer be any danger of a radioactive accident or to any persons visiting it. After a facility has been completely decommissioned, it is released from regulatory control, and the licensee of the plant no longer has responsibility for its nuclear safety. Historic accidents. The nuclear industry says that new technology and oversight have made nuclear plants much safer, but 57 small accidents have occurred since the Chernobyl disaster in 1986 until 2008. Two-thirds of these mishaps occurred in the U.S. The French Atomic Energy Agency has concluded that technical innovation cannot eliminate the risk of human errors in nuclear plant operation. According to Benjamin Sovacool, an interdisciplinary team from MIT in 2003 estimated that given the expected growth of nuclear power from 2005 to 2055, at least 4 serious nuclear accidents would be expected in that period. However, the MIT study does not take into account improvements in safety since 1970. Flexibility of nuclear power plants. It is often claimed that nuclear stations are inflexible in their output, implying that other forms of energy would be required to meet peak demand. While that is true for the vast majority of reactors, this may no longer be true of at least some modern designs. Nuclear plants are routinely used in load-following mode on a large scale in France, although it is generally accepted that this is not an ideal economic situation for nuclear plants. UNITA at the German Bible nuclear power plant is designed to win and decrease its output 15% per minute between 40 and 100% of its nominal power. Boiling water reactors normally have load-following capability, implemented by varying the recirculation water flow. Future power plants. A number of new designs for nuclear power generation, collectively known as the Generation 4 reactors, are the subject of active research and may be used for practical power generation in the future. Many of these new designs specifically attempt to make fission reactors cleaner, safer and/or less of a risk to the proliferation of nuclear weapons. Passively safe plants are available to be built and other designs that are believed to be nearly foolproof are being pursued. Fusion reactors, which may be viable in the future, diminish or eliminate many of the risks associated with nuclear fission. The 1600 MWE European Pressurized Reactor is being built in Olkiluoto, Finland. A joint effort of French AREVA and German Siemens AG, it will be the largest reactor in the world. In December 2006 construction was about 18 months behind schedule, so completion was expected 2010 to 2011. As of March 2007, there are 7 nuclear power plants under construction in India, and 5 in China. In November 2011, Gulf Power stated that by the end of 2012 it hopes to finish buying off 4,000 acres of land north of Pensacola, Florida in order to build a possible nuclear power plant. Russia has begun building the world unregistered trademark's first floating nuclear power plant. The £100 million vessel, the Lomonosov, is the first of 7 plants that Moscow says will bring vital energy resources to remote Russian regions. By 2025, Southeast Asian nations would have a total of 29 nuclear power plants, Indonesia will have 4 nuclear power plants, Malaysia 4, Thailand 5 and Vietnam 16 from nothing at all in 2011. Expansion at 2 nuclear power plants in the United States, Plant Vogtle and VC Summer Nuclear Power Plant, located in Georgia and South Carolina, respectively, are scheduled to be completed between 2016 and 2019. The 2 new Plant Vogtle reactors, and the 2 new reactors at Virgil C. Summer Nuclear Plant, represent the first nuclear power construction projects in the United States since the 3 Mile Island nuclear accident in 1979. See also. References. External links, IPPNW, International Physicians for the Prevention of Nuclear War, MAPW, Information on Australia's Research Reactor, Freeview Video Nuclear Power Plants, What's the Problem? A Royal Institution lecture by John Collier by the Vega Science Trust. Non-destructive testing for nuclear power plants, web-based simple nuclear power plant game, uranium.info publishing uranium price since 1968. Information about all NPP in the world, U.S. plants and operators, SCKCEN Belgian Nuclear Research Center in Mol. Civil liability for nuclear damage, World Nuclear Association, Glossary of Nuclear Terms, Protection against Sabotage of Nuclear Facilities, using morphological analysis and revising the design basis threat from the Swedish Morphological Society, Critical Hour, 3 Mile Island, The Nuclear Legacy, a national security online book by Albert J. Fritsch, Arthur H. Purcell, and Mary Bird Davis. Updated edition June 2006, an interactive VR panorama of the cooling towers at Temelin Nuclear Power Plant, Czech Republic, interactive map with all nuclear power plants US and worldwide, map with all nuclear power plants US and worldwide.